But then let me continue without talking too much. We're going to take another question. And the way I'm selecting these questions, guys, I'm trying to pick ones that are discussing or helping you in terms of like addressing more concepts. Like if somebody asks this and somebody else asks something else, I'm going to try and merge those concepts in one question. So I'm going to take Buhle's question, Buhle machine in it, and upgrade it a little bit by adding some of the things that were not really part of her question because you guys were asking them, right? Instead of doing the same thing 3 times, let's just use one thing to try and iron out everything and help you with the challenges that you might have, because this is the guarantee. The questions will never repeat, but the concept will repeat. You will never see the same question in any exam, but you'll see the same concept following. That's why we don't teach for the test here. We don't teach you to write tests. We teach you to understand the concept. Have a deeper understanding of mathematics because it's very beautiful, right? So I want you to have an understanding of what is going on. So the next question that we are going to look at is from Buhle Machine. I'm going to upgrade it a little bit, Buhle, sorry with that. So it reads as follows. Let's just see what is going on. It says to us that we are given the legend, f of x equals to 3 to the power of x, and, right, g of x is equal to that. Right. And now they saying something very exciting here. They say number 1, we need to find, this is actually where the exciting stuff happens, find the equation of g of x. Very powerful, right? Now you'll notice that we have now jumped to exponential graphs. And the second part of this, they say that we need to sketch on the same set right? On the same set of axes, it's a Cartesian plane on a Cartesian plane, both f of x and g of x. Powerful stuff, right? Absolutely exciting. Very, very exciting question. So f of x equals to 3 to the power of x and g of x equals to the inverse of f. Very powerful. Now, let's start first of all by answering the first part of this question. By now, you all know, the whole country knows by now, everyone who's watching the show, who's watching Tenfold live knows that the inverse graph is found by swapping x and y. And I know that there's some people also who are watching all over Africa, because I saw one of you guys posting on Facebook that you're from, I can't remember the country. I can't remember what country it was, but somebody was watching Tenfold live from another country. Big shout out to you. Please post again so that we can send love to you guys if you're not watching from South Africa. But for those of you who are here locally with us, thank you for joining. But then I hope this is also going to help you to understand as far as math is concerned, because math is the same. It doesn't matter where you are. Okay, now for the solution of this, I hope everybody who's watching now remembers that if you want to find the equation of g, you are actually looking for the inverse of f. And for you to find the inverse of f, you just have to swap x and y. That's all you're doing. So I'm going to begin my solution by saying f of x was given to us as 3 raised to the power of x, right? Now, that means we can rewrite this as y is 3 to the power of x. And this is where problems begin. This is a big, big problem, particularly if you haven't really been exposed to how to solve exponents by using something called logarithms, right? So I just expressed my f of x as y is 3 to the power of x. Now my process of finding the inverse says I need to swap them. So I haven't swapped them. So where I see y, I need to write x. And where I see x, I need to write y, right? Now this part is not complicated. Everybody understands this. Now the problem is making y the subject of the formula now. It's an exponent. How do you drop an exponent and put it as the subject of the formula in this equation? And what needs to happen now is you'll need to engage what we call the concept of logarithms. This is something that was discovered by a guy called John Napier, right? So John Napier came up with a very exciting idea, and the way he was thinking about it was complicated. Even to this day, I still don't understand what was in his mind that led to him being able to work out with logarithms. And that process was actually about finding ratios, because in the olden days, they didn't have calculators, guys. In the olden days, in the 1500s and the 1600s, they didn't have calculators. So during that time, they could add. Addition is not complicated, so they had to do things manually all the time. Like mental mathematics was the order of the day. Now, if you have to do mental mathematics in addition, it's not complicated, it's easy. But imagine if you have to do mathematics in multiplication. I can give you 3.2 and ask you to edit with 5.7 and ask you to edit with 9.1 and ask you to edit with 6.7. You won't have problems with that. But imagine if I said 3.2 times 4.7 times 9.1 times 6.7. This is a problem. This is a big problem. So this is the problem that they had, and Napier was interested in solving this problem by trying to convert multiplication back to addition, because what multiplication is essentially repeated addition. Because if somebody says to you, what is 2 plus 2 plus 2 plus 2, what they're saying to you is you can express that in short by changing addition to multiplication and rewrite that as 2 times 4, because the result of both those are actually equal to 8. So when you're saying 2 times 4, you're asking how many times can I add? If I add 2 to itself 4 times, what will the answer be? That's what you're actually asking when you're asking what is 2 times 4. So 2 times 4 is literally translating to how many times can I add 2 to itself? Oh, no. If I add 2 to itself 4 times, what will the result be? Yes. So multiplication is what we call repeated. Yes, repeated addition. Multiplication is repeated addition. So 2 times 4 means 2 plus 2 plus 2 plus 2 4 times. So what Napier wanted to do is he wanted to use this idea to convert multiplication back to addition, because it's easier to add stuff than it is to multiply stuff. So that's why he came up with a table that was called a logarithm table, and everybody was using it. And that table of his was derived from some ratios that he had came up with. And if you think about it, it was actually ratios of arithmetic values, right? Ratios of arithmetic values, which translate in Greek to literally logos arithmos, right? Logos arithmos. And this is where the name logarithms comes from, right? Logarithms. So we're doing that because of Napier, right? It was ratios of arithmetic values, which in Greek translate to logos arithmos, which then when you combine, you get what we call logarithms. So how do logarithms really work? They are essentially a process of working out or a different way of looking at exponents. So if you have this and you want to figure out what the exponent is going to be, right, you can introduce a logarithm on both sides. There are laws of logs that you can use here, because you people are watching Tenfold live. I will not cheat you. I'll show you the actual process of working with logs. Right. So let's take a smaller space here and explain something very exciting before we come back to simplifying that problem, right? If I gave you a problem such as 2 to the power of x is equal to 8. Everyone can solve this who is in grade 10, 11, or 12, because you guys will tell me, well, sir, just change 8 to exponential form and write it as 2 to the power of x equals to 2 to the power of 3. When the bases are the same, you can then equate the exponent, so the x value is supposed to be 3, right? Now this works well, we don't have a problem with that, but the problem starts when you can't change 8 to base 2. For example, if I had a different base, for example, let's just say we had 2 to the x equals to 5. So you can't change 5 to 2 to the power something, and this is why the logarithms become useful, because then they help you to work out the exponent, right, without struggling, because they are a nice way of working out exponents if you can't change the bases to force them to look the same, right? That's what exponents are all about. Now, logs. How would I use logs to solve the same problem? How would I use logs to solve the same problem? Well, to solve this problem, in order to try and find 8, what I'm going to do is I'm going to introduce logarithms on both sides of the equation. So what you do is you put a log on the left and you also put a log on the right hand side. I essentially did nothing there, because the law of conservation in mathematics says what you do on the left, you need to also do on the right hand side. By the way, log is short for logarithm. We are lazy as mathematicians. We pride ourselves with laziness. Now, the introduction of a log allows you to drop the exponent. It's like what I normally say to my learners is I say, you log in and then you download the exponent. So you log in. After logging in, I'm going to download that exponent. When I download that exponent, I'm going to get x log of 2 is equal to log of 8. And once I'm there, I can then divide both sides by log 2. Because if I divide on the left-hand side, right, by the log of 2 and divide on the right by the log of 2, my x here will come out as log 8 divided by log 2, since this will cancel that. And these can be compressed and expressed as 1 log, with 8 being the same size, and that 2 on the denominator is what we call the base of the log. We write it as a small number right there in the bottom. Right, so this is how logarithms work. I'm sure you're excited about this idea. You want to see another example. Let's just do another quick example, because this is a very important concept which is new to you. You probably don't know how it works, but it's going to help you to work out exponents if you need to work them out. Here's another example that I might be interested in. Suppose I have to solve 3 to the power of x equals to 81. Let's take 81. Right, let's take 81. And if I want to work out what x is going to be, we know that x has to be 4, because 3 to the power 4 is 81. So how would I use logarithms to try and figure out that exponent? The problem is we want that exponent to come down in order to find a solution to that, right? And I'm only using 2 laws of exponents. There are laws of logs. There are many laws of logs, but the ones that I'm using in this problem are only 2, right? So what I do, like I said, is you start by logging in. So let's log in. You log in. And if you log in on one side, you need to log in on the other side, because math says what you do on one side, you need to do on the other side. So this is log of 3 to the power of x is the same as log of 81. You just put logs on both sides of the equation. So after logging in, you can download. So let's download our exponent. So I'm downloading that x, it comes to the front. When I download it, I'm going to have x log of 3 equals to log of 81. And then you can then divide both sides by log of 3 divided, because you want x to be left alone. That cancels out, and you've got x is log 81 divided by log 3. Too many logs, there's a law that says you can just express them as 1 log, and the big number on top stays the same size, and the number at the bottom becomes the base of your exponent. There's a shortcut to this, but it's actually something that doesn't explain what is happening. It hides away all the math that is going on there. So this is what I prefer to show you what happens, so that you guys don't cram, but you understand the math that you are working with here. Very powerful. So let's go back and use Napier's idea to make y the subject of the formula, because we are looking for the equation of the inverse. All right, so I want y to be the subject of the formula, which means I want y to come down. But the only way you can download stuff is if you log in. So let's log in. I'm going to log on the left, right? I'm going to log in on the left, right? I've got log of x equals, I need to also log in on the right hand side, log of that 3 to the power of y, right? Once you've logged in, then the exponent can come down. You can download now. Let's download our exponent. So the y gets downloaded to the front there. It is going to then lead us to the log of x is y times the log of 3. A log is a function, so you do not actually cancel log with log. You just divide both sides by log 3, and you divide by log 3, right? And what is happening here is that log is not cancelling log and 3 is not cancelling 3. This is a pack. It goes as a pack. It's one thing. It's a unit, right? Just like if you've got the sine of x divided by n, you can't say, or maybe if you divide by sine, you can't cancel sine and be left with x. That's illegal, right? A sine is a function that is a unit like that. It's combined. It's one thing. It's an operation that does an operation on x. So even a log does an operation on 3. So you can't have a log flying around on its own without an argument. So log of 3 divided by log of 3. So the whole thing cancels the whole thing. They're not separate. They're one combined entity. So that cancels that as a whole. So even here, I can't say log cancels log, right? But what I can say is I'll say on the right hand side, I have y. And on my left, I've got too many logs. So we're just going to write 1 log, and the number on top stays the same size, and the number at the bottom becomes the base of your logarithm. That small number is what you call the base of the logarithm. So y is log x base 3, which I can then say my equation for g of x is just the logarithm of x with the base of 3. Very powerful stuff. So this is how you work with logs. I hope this has helped you gain more knowledge and understand something that is what we can imagine as something new. So please allow me to remove this side writing, which has just helped us to gain more knowledge on how to work out the values of exponents. Right. In case you're wondering, where is this log on my calculator? Well, if you call back your calculator and look at it, there it is. Maybe let's go back to that first question that I gave you to show you that indeed the answer to log 8 base 2 is going to be 3. If I call back my calculator, the log button, there's 2 of them in total. There's the one below the on button, top right corner, there's an on button. Directly below the on button, there's the log there. If you press on it, it will give you a log and a small box at the bottom for the base and a big box at the top for whatever the argument value is going to be. So in this case of log 8 base 2, I can put small 2 there. And then if you press the right arrow, it will lead you to the box inside brackets, which I can then put the argument 8. When I press the equality sign, I end up with an x of 3, which proves that indeed 2 to the power of 3 does give you an answer of an answer of 8. Right, so that's how you would actually use logs. The other log that you see, there's another log below the setup button, below there, the x to the power minus 1. That log with nothing next to it is a log with a base of 10, and it's for historical reasons that it's here. We'll share this information with you some other time, but it's because of historical reasons that it's happening to be there, and it has a special button. Please pay attention to that. Right. Okay, cool. So yeah, let's go on to the next question. We are still doing functions. We are doing grade 10, 11, and 12's work. I hope you guys are learning a lot of very exciting things in this. So the next question was about sketching. We just found the equation of g of x, and it came out as the logarithm of x with a base of 3. With a base of 3, yes. With a base of 3. Now we need to sketch these graphs. So exponential graphs, I always encourage my learners to use a table to draw them. We need to sketch them, right? We know that f of x is 3 to the power of x. We also know that g of x is the log of x with a base of 3. And we know that g is the inverse of f. So what I'm going to do is I'm going to draw a table for f, right? And I don't want a lot of values. I just want a few of them. I just want x values from, just say -2, -1, I want 0, I want 1 and 2. I already know the shape of 3 to the power x, but this is just for your education, in case we have some of you who still need to see this thing happening so that you have a much solid idea of what is going on. So I'm going to call my calculator, right? And remember what we do is we just have to substitute the values of x everywhere we see on that particular graph. So what I'm going to do is I'm going to use my table method on my calculator, another skill that you are donating on this show, how to use a calculator to complete tables. So on the top right corner, the button next to the on button is the mode button. You push that button there, right at the top, right? The second last button at the top right corner. You press that button, it will show you 3 options: comp, stat, and table. So I'm interested in building a table. So I'm going to press option 3 here, which is going to give me f of x, right? Once it does this, I'm going to type in my graph, which in this case, the equation was given as 3 to the power of x. So I push in 3, and then I need to put an exponent. So there's a button with x to the power of a box there, which I'm going to put there. It's going to give me a box, and then I want to now put x there. Now, x is a number, or it's a variable that is appearing in red on my calculator. So everything that is appearing in red, if you want to use that function, you need to press alpha first. If you want to use any function that is appearing in yellow, you need to press shift first. So that's the purpose of those 2 buttons. If you want to access anything yellow, you push shift first. If you want to access anything red, you push alpha first. So I'll push alpha, and you can see my calculator shows alpha there at the top left corner. And then I'm going to select x, which is by the bracket, the closing bracket. I push that closing bracket, it puts x there. And then I can press equal to. Now my calculator is asking me, where do you want to start your table? I'll tell it, well, I want to start the table at -3. Not -3, but -2. And then you press equal to. It asks, where do you want to end the table? I want to end it at 2 equals 2. Then it's asking, what steps do you want to use as you're moving from one value of x to the next? I want to keep 1. So I'm going to press equal to, and then my graph is going to give me a nice table with x values and f of x values. So you will notice that when x is -2, the y value, or the f of x value, is 0,11, which I'm going to write as my y values here, 0,11. Let's call it back, come back. And when x is -1, my f of x value is 0.33. Okay, so I'm going to say 0.33. It's a small number. Obviously, when x is 0, my y value is expected to be 1. When x is 1, my y value must be 3. When it's 2, I'm supposed to end up with a value of 9. Let's confirm indeed that the calculator does give us this. If you press the down arrow, it will keep showing you. For 0, we have 1. For 1, we're going to get a y value of 3. And for x is 2, we're getting an f of x value of 9. And that's the end of the table because we told the calculator to stop there. If you want to go back to normality, you just push the mode button again, and then you press the button comp 1, then it takes you back to normality. That mode button plays around between this format, the table format, and the statistics format. So I hope you guys learned something of using this table to draw graphs. You can also use it to draw trigonometric graphs if you ever want to do so. It just helps you and prevents you from typing things one by one because it wastes a lot of your time. Okay, cool. So let's draw that on a Cartesian plane. I'm going to have an ugly Cartesian plane that looks somewhat like that. Please bear with me. And I have got -1 here, and I have -2 here. I might have 1, I might have 2, I might have 3, right? I need a lot of y values because I need to get to 9. So I need 1, 2, 3, 4, 5. Okay, I'm not going to get to 9. Okay, 6, whatever. 7, 8, 9. Right. Let's just stop here. We'll cut it short. I hope you guys will get the idea of how the graph is going to look. Right. So when x is -2, where is my graph? When x is -2, my graph is very close to the x-axis. And when x is -1, the graph has increased a bit by some amount, but still very close to the x-axis. When x is 0, the graph is going to be at 1. When x is 1, the graph is going to be at 3. And when x is 2, the graph is going to be somewhere at the top at 9. So I can simply draw this graph by joining those dots nicely. All right, hopefully nicer than that. And then you can see the shape of your exponential graph coming out nicely there. That's the graph of f of x that we have right there. Right. Now I'm interested in drawing the inverse graph. Of course, this is the point 3:0. You might be nice to the examiner and tell them that this graph is passing through. That we can see that. Maybe here just put that it's 1 and 3. We'll really appreciate that. Right. Now the inverse graph, I'm going to be very naughty for drawing the inverse graph. I want to build a table for that. Why? Because you guys know already that the inverse, since this is the inverse of the graph of f of x, what I need to do is just swap my table values. Very, very nice. So what I'm going to do is I'm going to say for this next question, here's my table. I will not struggle and stress myself with any calculation. I'll have x's and y's. All the values I've got for x, that -2, -1, 0, and 1 from the yellow table, they will all be my y values. So I'll have -2 here, I'll have -1, I'll have 0, I'll have 1 and 2. So all x's become y's. That's the story with finding inverses. And all y's become x's, so those values are going to now become x values. So 0.11 here, 0.33 here, 1 here, 3 here, and 9 there. So let's try and plot all that. Let's plot that on the Cartesian plane. It seems like we will need to also extend our x-axis because there's more x's now. We need 4, we need 5, we need 6, we need 7. We could probably get to 9 if we want to because we've got enough space there. Right. Okay, cool. So then this side we've got -1 and we've got -2. Right. So let's see how the blue graph is going to fare. Okay, when x is 0.11, y is -2. So that's just to say -2 responds to 0.11. So -2 and 0.11, they meet somewhere there because -2 is there by the y-axis and 0.11 is very, very close to the y-axis. If you go to y value of -1, you will see that it's going to be 0.33. The x's are improving a bit, but not too much. But when x is 1, y is 0. That is happening here. When x is 3, y is 1. That is happening here. And when x is 9, y is going to be 2. So that's happening somewhere there. And then we can then draw the blue graph and we're going to get something nice that looks like that. Remember, the asymptotes of both these graphs are the y-axis and the x-axis. For example, the yellow graph will never touch the x-axis. That's the asymptote of the yellow graph. This here is the asymptote of the yellow graph. If I wanted to write the asymptote of the yellow graph, I'm going to say it is given by y equals to 0. But the asymptote of the blue graph, if I want to write the asymptote of the blue graph now, the asymptote of the blue graph is going to be the y-axis. It's this one here, right? Because it will never touch it. It might increase, it might decrease going down lower and lower, but it will never, ever, ever, ever touch the y-axis. So if I wanted to write, I'll just say the asymptote, right? The asymptote of the blue graph is going to be given by x is equals to 0. Again, see the beauty there. In the original graph, the asymptote is y equals to 0. In the inverse, the asymptote is x equals to 0. Once more, what is x becomes y and what is y becomes x. I've got another point that I want to put on a Cartesian plane, which is this point here. I want to put the coordinates of that. When x is 3, the y value is 1. And look at this, guys. Look at this. Compare that with the point I wrote in yellow there. This point that I wrote in yellow here, right? The point 1 and 3 is actually the opposite to the point 3 and 1. What was x and y have swapped to become y and x in the blue graph. So that's essentially the story about inverse graphs. It actually helps you to understand what is going on. But like I said before, be nice to people by writing down the line y equals to x. That passes at a point when x is 1, y is 1. When x is 2, y is 2, 0 and 0, minus 1 and minus 1, minus 2 and minus 2. This line is a crucial line because this is the mirror line, right? The line of reflection, that these lines are images of each other. And it is the line y equals to x. So please be nice to us and always put that line of reflection if you have to draw a graph and its inverse on the same set of axes. And this actually concludes what we wanted to discuss as far as this is concerned. Maybe we can be nice and write down the stories of the domains and the range for both f and its inverse. So if I go back again and I say, let's just make a table and say domain, right? And then put the range here, okay. And then I'm going to do this as a table so that you guys will see what is going on. It's the same story, nothing special here. On the graph of f of x, which is the original, and the inverse graph, right? The inverse graph. This one is the graph 3 to the power x, and the inverse graph is the g graph. The graph of g of x equals to the log of x with a base of 3. It's the inverse of the original. So the domain is asking for the x values on the yellow graph. Yellow graph. Let's go back to the yellow graph. Does the yellow graph have limitations moving left and right? I don't think so. I think it goes as far left as it wants without any limitations. So it's going to negative infinity. And if you look on the right hand side, even though it's going sharply up, but it does eventually go as far right as it wants without any limitations. So it means it covers all the x values. So for the domain, I'm going to say x is the element of real numbers. For the range, the yellow graph does not appear on the negative y values. It's from 0 going up only. It only goes up. From 0, it goes up. That yellow graph is not defined below the x-axis. It's only from the x-axis moving up. So it's from here going all the way up. So which means it's covering all values of y that are greater than the asymptote. And it's always the case. Always y is greater than the asymptote. Not greater or equal to, because graphs do not reach the asymptote. Now the range is going to be the opposite, which means, the domain and the range of the inverse. The domain and the range of the inverse are going to be opposite. So which means if you're asking me for the domain of the blue graph, I'm going to steal the range of the other one. I'm going to say x is greater than 0. Does this make sense? Yes, it does. Look at the blue graph. It doesn't cover any of the negative x values. It is only defined from x is 0 all the way to positive infinity. That's where the graph is going, right? That's why I'm saying x is greater than 0. And I don't have the graph at 0, so I'm not going to put x is greater or equal to, because I will be suggesting that it touches the x equal to 0 line, which is a problem because that is actually the asymptote of this graph. And then lastly, I'm looking for the range. I'm just going to say y is the element of real numbers. Why? Because it actually covers all y values. It goes as far low as it wants and as far up as it wants. And then this actually concludes the analysis of working with an exponential graph and logarithms.